Dr. Valentina Taranovic is an early career economic geologist, geochemistry, holding a PhD from Indiana University, USA, and primarily studying magmatic nickel sulfide ores deposits worldwide. Most recently, she was a postdoctoral fellow within Commonwealth Science and Industrial Research Organization, CSIRO, in Perth, Western Australia. Prior to the last Nova nickel sulfide research work in Australia, she was an exploration geologist and university lecturer in the USA. Valentina is an advocate of sustainable and environmentally responsible mining practice and a gender equity in the mining industry and STEM fields. So thank you, Valentina, you can start.
Greetings everyone around the world. I will be giving you some of the story about Nova Bollinger nickel sulfide ore deposit in Western Australia, which was a part of my postdoctoral study at CSIRO. The talk that I will be focusing on today will be on mineralogy, textures, and geochemistry. And I'm going to go ahead and start on that by telling you the location of the Nova Bollinger ore deposit, which is in the Fraser zone of the Albany-Fraser origin, which is a major lithostratigraphic domain of the Albany-Fraser origin, which recorded Paleoproterozoic modification of the margin of the Archean Yilgar craton. So Nova Bollinger ore deposit located here is placed into a tightly folded sequence of pelitic to semitic gneisses and mafic granulates and gneisses and with local marbles, conglomerates, and iron formations. From one of the previous studies from Glasson et al., we have the estimated ambient conditions to be between 800 and 850 centigrade at about 7 kilobars ambient metamorphic pressure. So from what you can infer here is that this is a granulate fascist terrain, and we have some tightly folded rocks in which the Albany-Fraser origin has Nova as one of the major nickel sulfide ore deposits in place. So the Fraser zone is dated at 1310 to 1280 million years from one of the previous studies as well, and Nova Bollinger ore deposit formation age falls within that range. I will tell you a little bit about one of the questions that we've been trying to answer from the beginning and have successfully answered during the duration of the project, which is where in the crust location-wise Nova Bollinger ore deposit has formed. And the options obviously are somewhere close to the superficial environment, upper middle, or lower crust. And the reason why this question was important to answer was because, as anyone who studies these types of deposits knows, we have several different kinds of these deposits associated with different stratigraphic levels within the igneous systems, for which we develop different exploration strategies. So therefore, for exploring for komatiites and iron picrites hosting nickel copper ore deposits, we cannot use the same strategy as, for example, looking for Voisey's Bay of Jinshuan large intrusions with which we have associated different types of nickel sulfide ore deposits. So this was one of the questions that we were trying to answer from the beginning of the project. To give you a little bit more comparison between some of the major nickel sulfide camps, such as the Kimbalda camp, Norilsk, Sudbury, in terms of the nickel grade and resource estimates. This is Nova Bollinger ore deposit here, close to Savannah ore deposit, which is also in Western Australia and in some ways quite similar. There are quite a few previously done studies on Savannah, and we use it as one of the analogs because they're quite similar to Nova in some of the respects. And just to give you some of the numbers here is that the combined resource estimate for Nova is about 13.1 million tons of about 2% nickel, 0.8% copper, and 0.1% cobalt, which is an estimate from the last year by the Independence Group that owns these deposits and operates on further exploration. So now we come to the part of where my study had started, which was 3 years ago. Basically, what we have to work with was we had a luxury of having quite a few drill holes through the Nova Bollinger system that we could have chose from to look into more details, collect samples, and do all kinds of geochemical and other textural and mineralogical analysis. And these on this map are the drill holes that my samples are coming from. This is a schematic cross-section of east-west schematic long section of the Nova Bollinger and the host rocks with the location of the drill holes that are falling into that section, showing the locations of the samples from isotopic studies. Most of the yellow stars are actually sulfur. I will talk about that later on, but what I wanted to show here is the general shapes and locations of various important units within the system. So on the top here, we have the upper intrusion, which is bowl-shaped, and it's composed of mafic and ultramafic rocks interlayered one with another, with this lower basal zone of predominantly composed of norites and gabbronorites, and this C5 mineralized zone, which is predominantly a disseminated type, below which we have the lower intrusion that is a mafic to ultramafic lithologies dominated channelite. So it's a differently shaped intrusion. Below which we have bulk of the ores emplaced into the country rocks. We have a Nova ore body located here and Bollinger ore body located here with all different ore types, massive, disseminated, and net textured. And what we have looked into for this particular study was the nature of the system in terms of being primary igneous or metamorphically and structurally deformed during or after the peak conditions of the Albany-Fraser origin. So what we've observed, I'll tell you right away, was that we are dealing with the primary magmatic textures within all the Nova rocks. So I'll give you quite a few of the evidence for that throughout my talk. So throughout the talk, I'll be using these XFM images, which are the elemental maps. Most of them have matched the color scheme for red to correspond to chrome, iron to correspond to green color, and calcium to be blue color. I've made a, excuse me, a mineral phase maps out of these maps as well. So I'll be going through the stratigraphy, starting with the Nova section, showing you the location of the sample and telling you a little bit of what those rocks actually are. So this is a layered peridotite. The lithology can vary up to olivine gabbronorite, and it's a typical rock of the upper intrusion where we can see these zoned oikocrysts of orthoclinopyroxene and orthopyroxene. These bright greens are the olivine grains. These bright blue color is the plagioclase. So all these muted colors in terms of the greens and blues are actually this interesting symplectitic assemblage that I will also be explaining a little bit more about, and it's basically a combination of two or more minerals caused by a couple of the minerals reacting one with another. You'll hear more about that as well. So moving down to the stratigraphy, this is slightly lower in the section, how a typical norite, gabbronorite of the upper intrusion looks like, where we have the typical cumulus pyroxene orthocumulate kinds of rocks, where we get to see thin hornblende biotite overgrowths. We can get to see some of the hornblende biotite rimming pyroxenes. We do get to see some of the microstructures as well, such as the bent or strained grains. We get to see some of the spindle twinning, and all of these features we can easily attribute to strain during compaction of the cumulus spine, but this texture as well we interpret to be a primary cumulus kind of a texture. Going down into lower into the stratigraphy, here is the Nova section, typical lower intrusion rock, the same color scheme here, where you can see pyroxene dominated cumulate rock as well, with the same chrome zoning into the orthopyroxene and clinopyroxene. It's much like in the upper intrusion, fairly similarly looking like rock as well. And here are some of the mineralized rocks, just for the for showing how those actually look like as well. So the part that isn't mineralized contains some of the green spinels, which are actually the cumulus phase. We have early formed chromite inclusions in the olivines. We have pyroxene oikocrysts that have primary exsolutions, and there's quite a few of these sulfide embayment textures into olivine grains. So this is a typical lergolite peridotite with patchy net texture to disseminated sulfides. We do have symplectite assemblage throughout here as well. So this would be shown here and there, which will be shown much better in slides to follow. Here as well, we get to see some of the deformation twinning in the pyroxene too. And I've shown here a couple of reflected light images of the typical pyrrhotite plantaline chalcopyrite plus magnetite magmatic nickel sulfide ore deposit assemblage, where on a thin section scale, we do get to see some of the chrome-rich domains versus nickel iron rich domains mineralogies on a sample scale in some of the cases. Here's another sample of the net textured sulfides in a fine grained peridotite, which I should point out as well that all of the olivines and pyroxenes are fresh throughout the system. You can see again here some of those green cumulate spinels. And I should point out that the actual patches are clumps of olivines. They're not oikocrysts. They're clumps of fine-grained olivines, which are sulfide-free. And here you can see this other interesting type of sulfides, which are symplectites, which is a sulfide silicate symplectites, which we didn't get quite into working out throughout this study. So we have oxide silicate, silicate, and sulfide silicate symplectites within the system. Moving down into the stratigraphy in Bollinger section, here is the upper norite to gabbronorite intrusion rock, how it looks like here. We most importantly observe the texitic of very textured nature of these rocks, where we get to see, in this particular case, fine-grained edges and coarse, almost pegmatitic-like orthopyroxene plagioclase cumulate patches. So the difference between the fine grain and the coarse grain version is just the size of the crystals. There is no mineralogical textural difference between the two, and you do get to see the chrome zoning in pyroxenes in both of these cases. Slightly lower in the Bollinger section, we observe primary magmatic layering in the upper intrusion, which is subhorizontal, and in this case is defined by the cumulus orthopyroxene and poiklitic clinopyroxene and orthopyroxene. So this is a layered peridotite from the Bollinger section. Moving down in the section again, we get to see the same subhorizontal layering in norite and gabbronorite part of the upper intrusion, where this this layering is defined as the chains of non-aligned grains. It's not a foliation. So this is a cumulus texture, and this is a layered gabbronorite with primary magmatic layering, subhorizontal in nature at the Bollinger section. This part here is from one of the underground exposure mapped by Jim Miller of CSIRO in 2018, where in one of the sections that he had mapped, we have observed again the subhorizontal primary layering, which is defined by the lamination of olivine in the planes of the primary layering. So this type of layering subhorizontal in nature, we also attribute to gravitational settling in the small dynamic systems such as the conduits, because otherwise it cannot be produced, because in large magma chambers such as the Skaergaard complex, for example, due to convection, this type of layering can be formed at the edges of the intrusion, but not in such a small system in terms of producing this type of layering. So we attribute it to primary regional layering. So moving on to the moving on to the chrome zoning that we get to see throughout the whole system, we see this to be characteristic magmatic polyclitic textures where obviously our olivine and orthopyroxenes are cumulus, and we get to see sector zoning, oscillatory zoning. It's evident throughout the system in pretty much most of the rocks. So we started observing these at different places, and people before us have been observing in different places throughout the world. However, they might have been observed at other places as well, just not explored for or looked at yet. So the way we describe how these complex patterns have formed is from basically poor mixing of the magma in a dynamic system where the magma is interacting with the wall rocks to produce these complex pattern of zoning in some of the crystals. And they are basically due to silica differences in silica activity, composition, and redox state. And we try to see if this is a characteristic feature of mineralized systems, or if this is a feature that just occurs in very well-mixed systems around the world. And there has been follow-up studies on this at CSIRO and other places, I'm sure, as well. The symplectite stories are quite a bit interesting as well. So we notice there's this funny assemblage of small interlocking grains of various minerals, in some cases forming coronas as well. And then we followed up with looking into what kind of minerals are participating in these reactions and whatnot. So this is what we have found out, that the symplectite is basically a reaction where we have olivine and plagioclase that are obviously unstable in this assemblage, reacting with the melt to produce hornblende spinel and orthopyroxene replacing plagioclase. So this is one of these symplectites, how we have formed. And we went even further on and analyzed these rocks at the Australian synchrotron, and this is the enlargement to which we can actually see these inner growths of minerals one with another. To explain this, I won't go into too many details, but I will tell you that everything has to do with phase equilibria at different pressures, basically at low versus different pressures. And this is the key point here. And that is that at low pressures, we have olivine and plagioclase happily co-precipitating one with another. But as soon as you ramp the pressure up from 8 to 10 degrees, that cotectic disappears, and all of a sudden, olivine and plagioclase are not happy one with another. So what happens is you have cumulus spinel crystallizing along with olivine, and then plagioclase joins later on during the crystallization. So you can technically have olivine and plagioclase in the same rock, but they won't be in equilibrium one with another at those pressures. So you start breaking down and forming symplectic type assemblages that we observed. So we have a follow-up study on that as well by Torres Rodriguez, who estimated the pressures of this reaction to be taking place between 7.6 and 9.6 kilobars. And so there was a thermocalc study follow-up to this, and this is what we came up with. I'm going to move on to the mineral chemistry. We analyzed most of the major minerals in the system, and we were trying to answer some questions such as the temperatures and pressure, what kind of processes we've been able to identify using the mineral chemistry. What are the nickel data suggesting about nickel sulfide saturation? In this, we have analyzed olivine chatacrysts or inclusions of olivine in pyroxenes, as well as the cumulate olivine grains. We analyzed the spinels, which are the cumulate spinels that we find, the green ones within the rocks, and as well as the inclusions of the early formed inclusions of chromite in olivine. And I'm showing here just the olivine data, where you can see that the Mg number goes up to 85. The average is about 83. Obviously, the mineralized rocks are more fractionated, so their average Mg number is 77. The nickel content of the lower intrusion, which are these rocks here, goes up to 1400 ppm. And on this trend, you can observe The upper intrusion rocks, which are here, most of which are following the fractional crystallization trend, but we do have some that correspond to sulfide depletion trend. Obviously, the mineralized rock would have the nickel enrichment trend, which are mostly the rocks of the lower intrusion. And on the global nickel map, we see that the Nova Bollinger olivines are slightly lower in their nickel content compared to the global average. So in terms of spinel chemistries, all of our Nova spinels are actually aluminum rich. So this is where they belong to. They're quite far away from the global average values. And in this respect, they correspond to the high pressure alpine ophiolates. So orthopyroxene data is showing the same, which is that the aluminum contents was high and consistent with the high pressure crystallization, as well as the spinel data. And I'm going to move on here because I have a few more things to say. In terms of crustal contamination, we were looking for distinct geochemical signatures, which could be recognized on regional data sets and regional scale to obviously look for more of these types of systems that have a potential to host large volumes of sulfide. So we looked into silicate portion of the system and sulfide portion of the system using whole rock trace element geochemistry and isotopes. Right off the bat, I'll tell you that the silicate portion of the system did not record much, if any, crustal contamination. This is the lower intrusion rock, the upper intrusion rock, fairly flat, non-contaminated signature patterns, where we can only see the difference between the amount of trapped liquid. So one is the orthocumulative nature, the one is the adcumulative nature, and that's the only difference between the two. If we try using some of the highly incompatible trace elements ratios, such as niobium, thorium, lanthanum, samarium, to try to roughly model the crustal contamination in silicates using the primitive mantle and one of the Snowy's Dam metasedimentary rock, which is the footwall lithologies to the Nova Bollinger ore deposit, we can pretty much calculate that most of the rocks can be produced via bulk crustal contamination of about 0.5 to 5% of the crustal contaminants. So that's a fairly low degree as well. Looking into isotopic systems, I'll show you the data for sulfur 34. We have analyzed sulfur 33 as well, strontium, samarium, neodymium. I won't be showing that data today. But here are some of the images of the typical footwall metasedimentary country rocks, which is, some of them are quite calcite rich. So this is a marble. It's actually a contact between the pyroxene footwall gneiss and the marble, where you can see a lot of calcites, and here finely grained pyroxenes and garnets. And then this is the plagioclase quartz garnet footwall gneiss, where you can see these very nicely formed garnets with silicate inclusions, small inclusions forming during their growth. There are lithologies that contain some of the sulfides, which we have analyzed as well. So this is the map of the isotopic samples for sulfur as well, where we try to cover most of the system, and also analyzing some of the country rocks that did contain the sulfides, unlike these two examples that I've just shown. So this is the sulfur 34 isotopic data, broken down into Bollinger, Nova, and the Snowy's Dam formation. So the range of sulfur 34 for Snowy's Dam formation is anywhere between about 2 and 7.2. So this range is more narrow than what we have recorded in the rocks. For example, here's the Bollinger, the range of values from 1.6 to 8. There are differences between the Nova and Bollinger in terms of these values. So the average for the Bollinger rocks is about 2.8, let's say, and the average for Nova rocks is slightly higher. There are some of the differences within these ranges as well. What I haven't shown here was the C5 intrusion and the lower part of the upper intrusion belonging to norite and gabbronorite, because these values are falling within the upper intrusion and completely are being within this range, so they would not be well represented in this plot. So the bottom line is we see ubiquitous signature of crustal contamination with values between 1.6 to 8, slightly different average values for NOVA versus Bollinger. But overall, those are the values that we're seeing in the snowy dam formation as well. So they're not drastically fractionated value in any sense at all. Comparing the disseminated ores from NOVA versus Bollinger, as well as from the net texture and the massive sulfides, we do get to see some of the differences here. Again, the ranges are quite similar, except that we have this one high value here for NOVA for the disseminated, and we have a slightly larger net textured variation here. With the more samples being analyzed for the sulfur 34, these ranges might be changed. So they're not set in stone at the moment. For the comparison purposes, Savannah ore deposit has sulfur 34 values between plus 1.5 and 5 per mil, with the average value of 4, which is quite similar to Noah Bollinger as well. And another prospect called Octagonal, which is another prospect in the Albany Fraser belt, in some ways similar to Nova. We've heard from Walker and Evans just last year on some of the conference talks in Western Australia. Their values are quite similar as well, from +2 to +8 per mil. So again, everything is within the range of NOAA. So what we see here is that neither sulfur 34 nor 33 are strongly anomalous. And I will tell you about the sulfur 33 now, which is that the reason I haven't shown any plots from sulfur 33 is that none of the values were actually anomalous. All of them were within the analytical precision and accuracy for the analytical technique used. But then again, so were the values for the Snowy Dam metasedimentary country rocks. So possibly similar type of lithology was an actual contaminant. So we don't get to see this anomalous signature, or it has been somehow flushed out of the system, which is what brings me to the next point, explaining how the exchange reactions between the accumulated sulfides and new pristine magma within the system actually can flush out strongly anomalous signatures, and this originally probably recording quite larger variations in isotopic systems in terms of crustal contamination. So we do record extensive interaction with the country rocks. With all of these types of information being kept in mind, I'll give you a little bit more information about the petrogenesis of the system and where the actual Nova Bollinger rocks are formed. So if we take into considerations the following, which is the intrusion shapes, the upper intrusion formed in a bowl-like geometric shape composed of modally layered ultramafic and mafic rocks, and the lower intrusion being a chronolith-like system with the ores being placed mainly into the country rocks. We have the primary magmatic layering observed in the system. Lots of the petrographic information is very much so in favor of the primary magmatic cumulate textures throughout both intrusions. We have the phase equilibria explaining the presence of minerals and mineral assemblages during the high pressure crystallization. In terms of the crustal contamination, we have almost a complete evidence of this taking place in the silicate portion of the system. The sulfide portion of the system is telling us that, yes, there has been quite a bit of country rock interaction, accounting for the amount of sulfides and isotopic signature within the sulfide system to have been recorded. So for all these and other inferences that are not presented in the study, we have concluded that our system has been formed in the mid-crustal environment, syntectonic emplacement, basically during the peak metamorphic conditions of the Albany Fraser origin. This concludes my talk for today. I thank you very much for the invitation and this chance to present. I look forward to all of your questions. I would like to thank Independence Group for setting me up with this project and providing all the access and support throughout my postdoctoral appointment. I'd like to thank Steve Barnes and the rest of the researchers I've collaborated with on this project, and all of the other scientists and facilities that we had a chance to work with and collaborate throughout my study in CSIRO. Here's my personal email and my personal phone number. I'm no longer at CSIRO, so I'm not there in Perth. I'm in Serbia. And this is my former supervisor, Dr. Steve Barnes, and his current email and current phone number. You're welcome to contact us for any information, further information, and any other details you'd like about this study. Thank you very much.